So this is an AR model with complex roots, and it is certainly going to be complex for sure. Can you imagine that? All right, moving on. So consider an AR2 model, which is xt minus v1, xt minus 1 minus v2, xt minus 2 equals at. And of course, we could rewrite this as xt minus v1b, xt minus v2b squared, xt equals at, where b is the backwards operator. And if we pull xt out, we have 1 minus v1b minus v2b squared equals a sub t. So that right there is the characteristic polynomial. And let's rewrite that as phi of s equals 1 minus phi1s minus phi2s squared. And we'd like to find the roots of the characteristic polynomial, but before we move on, if we have complex roots, there will be oscillations in the ACF. But these oscillations are going to be damped in the sense as h increases, the autocorrelation would go to 0. Even though there are oscillations, it is not going to be oscillating forever. The ACF will approach 0 as h approaches infinity. So our goal is to find the roots of phi of s, the characteristic polynomial. So to find the roots, set phi of s equal to 0 and solve for s. So we are going to get as the roots to be phi1 plus or minus square root of phi1 squared plus 4 phi2 divided by 2 times phi2 with a negative. This aside, we don't care about this part right now. Rather, we are going to assume that the roots of phi of s are complex. And from the fundamental theorem of algebra, you should realize that if we have complex roots, occur in conjugate pairs. In other words, if we have a root a plus ib, where a and b are real numbers, then there has to be a root which is a minus ib. So a plus ib is called the conjugate of a minus ib and vice versa. That said, what if we had complex roots, and if we saw cases where we had distinct roots, distinct real roots, and we saw cases where we had repeated real roots? Now we want to find a general expression for Rho K where the roots are complex. So, things to recall. Phi1 in terms of the roots are R1 inverse and R2 inverse, and Phi2 is negative R1 inverse, R2 inverse. So if R1 is A plus IB, R1 inverse is 1 over A plus IB. So if we multiply and divide by the conjugate, which is A minus IB, over A plus IB times A minus IB, we'd end up getting A minus IB divided by A squared plus B squared, which is simply A over A squared plus B squared minus I times B over A squared plus B squared. And let us define R to be equal to the square root of A squared plus B squared, and this is what we call the magnitude of the complex number. In a similar manner, R2 inverse would be 1 over A minus IB, multiply and divide by the conjugate, so A plus IB divided by A minus IB times A plus IB, so we would get A plus IB divided by A squared plus B squared, which is simply A over A squared plus B squared plus I times B over A squared plus B squared. In short, we could write R1 inverse, which is alpha 1, as A over R minus I times B over R squared, and R2 inverse would be alpha 2, which is A over R squared plus I times B over R squared. So now that we have R1 inverse and R2 inverse, we could find expressions for Phi2, Phi1 and so forth. Since Phi2 is R1 inverse, R2 inverse with a negative, 1 over Phi2 would be equal to negative R1, R2, which would mean 1 over Phi2 is equal to negative take the value of R1 and plug it in here. So we would have, well, let's use the inverse part. We would have R1 inverse, which is A minus IB over R squared times A plus IB over R squared. I'm directly using Phi2 because that is going to be easier. So R squared Phi2 would equal to negative A squared plus B squared. It seems like we are going in circles, so give me 1 second here. Ah. So since we assumed that the roots are R1 and R2, and they are complex, we could simply extend the fact that the roots phi2 could simply be equal to alpha 1 times alpha 2 with a negative. Since R1 and R2 are complex numbers, so are alpha 1 and alpha 2. So this would imply alpha 1 is some a plus ib, and alpha 2 is a plus ib or a minus ib. So we would have phi2 equals negative a plus ib times a minus ib, which is negative a squared plus b squared. That would equal to phi2, which would imply phi2 equals negative r squared. So negative phi2 would equal to r, which would imply r is square root of negative phi2. So we found the magnitude in terms of the coefficient, the second coefficient, which is negative phi2. So now that we have that part sorted out, we have to recognize Oilless formula. So e raised ix is equal to cosine x plus I times sine x. So that is quite important. So since we know that we have two complex roots, let's take the first root, a plus ib. We could write it as r times we could write the first root as r times e raised I 2 pi f naught, and the other root as r times e raised minus I 2 pi f naught. Remember, when we do this, we are actually switching to polar coordinates. You don't have to pay too much attention to this if you haven't taken Calc 3, but do understand that all of this is coming from Euler's formula. Which is right over here, damn it. Right there. So what we can do now, so a plus ib, some complex number, is represented by e raised I 2 pi f naught. If we use Euler's formula, that would be r times cosine 2 pi f naught plus I sine 2 pi f naught. I'd mention what f naught is in a matter of time. So a minus ib would be r times e raised minus I 2 pi f naught. That would equal to r times cosine 2 pi f naught minus I sine 2 pi f naught. And we are going to add these two equations. So when we add, we'd end up having 2a is equal to r times cosine 2 pi f naught plus I sine 2 pi f naught plus cosine 2 pi f naught minus I sine 2 pi f naught. Those two terms would go away, and we'd simply have 2r cosine 2 pi f naught equals 2a. The 2's cancel, which would mean cosine 2 pi f naught would equal a over r, but we know that r is square root of a squared plus b squared, which would mean 2 pi f naught is cosine inverse a over square root of a squared plus b squared. If we continue, we would get f naught equals 1 over 2 pi cosine inverse a over square root of a squared plus b squared. This f naught is what we call the system frequency. And as I mentioned earlier, anytime we have complex roots, the series is going to have oscillations. So f naught will measure that oscillation. In other words, it is going to give you the frequency, and if we have the frequency, we know the period with which the function is oscillating. So now that we have this expression, we are going to find the general expression for Rho K. So the general expression for Rho K is Rho K equals C1 e raised, going one step ahead, R1 raised negative K plus C2 R2 raised negative K. But from other videos, we realized by setting alpha 1 equals R1 inverse and alpha 2 equals R2 inverse, we were able to come up with an equation for Rho K, which is alpha 1 raised K plus 1 times 1 minus alpha 2 squared minus alpha 2 raised K plus 1 times 1 minus alpha 1 squared divided by alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2. So what we're going to do is we're going to plug in alpha 1 and alpha 2. So again, alpha 1 and alpha 2 are complex numbers. So we can express them as r times e raised I 2 pi f naught and r times e raised minus I 2 pi f naught. Why? The reason being alpha 1 and alpha 2 always occur in conjugate pairs. So since they are conjugate pairs, according to Euler's formula, if one of them is r times e raised I 2 pi f naught, the other has to be r times e raised minus I 2 pi f naught in polar coordinates. So that said, we will say alpha 1 is r times e raised I 2 pi f naught and alpha 2 is r times e raised minus I 2 pi f naught. So plugging in the expression, and let's tackle the general expression numerator and denominator separately. So let's start with the numerator. So alpha 1 raised k plus 1 is simply r e raised I 2 pi f naught raised k plus 1 minus, 1 times r e raised minus I 2 pi f naught raised 2 minus r e raised minus I 2 pi f naught raised k plus 1 times 1 minus r e raised I 2 pi f naught squared. So that would give us r raised k plus 1 e raised I 2 pi times k plus 1 f naught, a rule of exponent, multiplied by 1 minus r squared e raised minus I 4 pi f naught minus r raised k plus 1 e raised minus I 2 pi k plus 1 f naught times 1 minus r squared e raised I 4 pi f naught. So in both terms we have r raised k plus 1 in common. So we would end up having e raised I 2 pi raised k 2 pi times k plus 1 f naught multiplied by 1 minus r squared e raised minus I 4 pi f naught minus e raised minus I 2 pi k plus 1 f naught multiplied by 1 minus r squared e raised I 4 pi f naught. We know from earlier that r is negative phi 2, which would imply r is square root of negative p2 right here, which would imply r squared is simply negative phi 2. So what I'm going to do is I'm going to replace r squared by negative phi 2, so I'd have 1 plus phi 2 e raised negative 4 pi f naught minus e raised minus I 2 pi k plus 1 f naught times 1 plus phi 2 e raised I 4 pi f naught. Now distribute the exponential. We have r raised k plus 1 e raised I 2 pi times k plus 1 f naught plus phi 2 e raised I 2 pi k plus 1 f naught times e raised minus I 4 pi f naught minus e raised minus I 2 pi k plus 1 f naught minus e raised phi 2 e raised I 2 pi k plus 1 f naught times e raised I 4 pi f naught. I just distributed the exponentials that are over here. Damn it. And I just took them inside the parentheses. I distributed them inside to get that term and that term. Moving on, so we have r raised k plus 1 e raised I 2 pi k plus 1 times f naught. I'm moving things around, so I have e raised minus I 2 pi times k plus 1 f naught plus phi 2 e raised I 2 pi k plus 1 f naught times e raised minus I 4 pi f naught minus phi 2, e raised I 2 pi k plus 1 f naught times e raised I 4 pi f naught. Oh, I forgot a negative here. So now we know e raised ix, according to Euler's formula, is cosine of x plus I sine x, right over there. So we go back and replace the exponentials in terms of cosine and sine. So the highlighted part here would be x, so we would have cosine 2 pi k plus 1 f naught plus I sine 2 pi k plus 1 f naught minus cosine 2 pi k plus 1 f naught minus I sine 2 pi k plus 1 f naught. Something to note here, Euler's formula also states that e raised minus ix is simply cosine x minus I sine x. So that is a side note, because the second term right here has a minus in the exponent, so I'm putting a minus there. And as we go, we have phi 2. We can combine the exponentials and write it as e raised I 2 pi k plus 1 f naught times e raised minus I 4 pi f naught minus phi 2 e raised negative I 2 pi k plus 1 f naught plus I 4 pi f naught. So as we expand, we can see we'll have cosine 2 pi k plus 1 f naught plus I sine 2 pi k plus 1 f naught minus cosine 2 pi k plus 1 f naught plus I sine 2 pi k plus 1 f naught plus phi 2 e raised I 2 pi k f naught plus I 2 pi f naught minus I 4 pi f naught minus phi 2, the very last term, e raised minus I 2 pi k f naught minus I 2 pi f naught plus I 4 pi f naught. So those two terms would go away. So we will have r raised k plus 1 2I sine 2 pi k plus 1 f naught. The second term, or the last two terms, phi 2 e raised I 2 pi k f naught minus I 2 pi f naught minus phi 2 e raised, this is the last term, minus I 2 pi k f naught plus I 2 pi f naught. So that would give us r raised k plus 1 times 2I sine 2 pi k plus 1 f naught plus v2 e raised I 2 pi times k minus 1 f naught. So I'm just pulling 2 pi f naught out of these two terms, that term and that term, which would leave me k minus 1. I'm also pulling out the I. Do the same here. We're going to pull negative I from those two terms in addition to 2 pi f naught. So we would have e raised 2 pi k minus 1 f naught. We are going to use Oilless formula one more time. So 2I sine 2 pi k plus 1 f naught plus v2 cosine 2 pi k minus 1 f naught plus I sine 2 pi k minus 1 f naught. Minus v2 cosine 2 pi k minus 1 f naught minus I sine 2 pi k minus 1 f naught. Distribute and simplify. 2I sine 2 pi k plus 1 f naught plus v2 cosine 2 pi k minus 1 f naught plus I times v2 sine 2 pi k minus 1 f naught minus v2 cosine 2 pi k minus 1 f naught plus I v2 sine 2 pi k minus 1 f naught. So those two terms are identical, so that those would go away, and these two terms are identical with positive signs, so we could combine that. That would give us r raised k plus 1 2I sine 2 pi k plus 1 f naught plus 2I v2 sine 2 pi k minus 1 f naught. We have 2I in common, so 2I times r raised k plus 1 sine 2 pi k plus 1 f naught plus sine v2 sine 2 pi k minus 1 f naught. We're not done yet. This is just the numerator. So we move on to the denominator. So the denominator is alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2. So alpha 1 is r times e raised I 2 pi f naught. Alpha 2 is r e raised minus I 2 pi f naught. 1 plus r e raised I 2 pi f naught times r e raised minus I 2 pi f naught. So we have an r in common, so we'd pull that out. So we have e raised I 2 pi f naught minus e raised minus I 2 pi f naught, and 1 plus r squared. When we multiply that term with that term, the bases are identical, the exponents are in opposing signs, so we would end up getting e raised 0, which is 1. And we'll have 1 plus r squared. But we already know from earlier that r squared is simply phi 2. So we will have r times e raised I 2 pi f naught minus e raised minus I 2 pi f naught multiplied by 1 plus phi 2. Using Euler's formula again, we could write the first exponential as cosine 2 pi f naught, because the x term is that, and likewise the x term is that in Euler's formula. So plus I sine 2 pi f naught minus cosine 2 pi f naught. And since we have a negative here, it has to be minus I sine 2 pi f naught. The entire thing is multiplied by 1 plus phi 2. So r times cosine 2 pi f naught plus I sine 2 pi f naught minus cosine 2 pi f naught plus I sine 2 pi f naught, and the entire thing is multiplied by 1 plus phi 2. Those two terms are identical and they have opposing signs, so they get cancelled. And these two signs are identical with similar signs, so we add them. So we have 2i sine 2 pi f naught multiplied by 1 plus phi 2. So 2i is in common, so if we pull 2i out, made a slight error here. Note r is square root of negative phi 2, which would imply r squared is negative phi 2. So that has to be a negative. So we would have 2i r sine 2 pi f naught times 1 minus phi 2. And that is the denominator. So the general expression for Rho K is simply the numerator that we found divided by the denominator. So the numerator is that term over there. So that is 2i times r raised k plus 1 multiplied by sine 2 pi k plus 1 f naught, which is right there, plus phi 2 sine 2 pi k minus 1 f naught. Just wanted to make sure that I plugged in the right phis. Okay. Didn't want to make the same mistake as I made over here in terms of r. And divide the entire thing by the denominator we found, which is 2i r sine 2 pi f naught times 1 minus phi 2. The two i's go away. The r, one of them, would go away. So we have Rho K is r raised k. sine 2 pi k plus 1 times f naught plus phi2 sine 2 pi k minus 1 times f naught divided by sine 2 pi f naught times 1 minus phi2. And since we know that r is equal to negative phi2 and square root, rho k would be equal to square root of negative phi2 raised k sine 2 pi k plus 1 f naught plus phi2 sine 2 pi k minus 1 f naught divided by sine 2 pi f naught multiplied by 1 minus phi2. Mind you, this 2 pi f naught is for the sine, and that is an entirely separate term. One last step, we could do some algebra and write it as negative phi2 raised k over 2 times sine 2 pi times k plus 1 multiplied by f naught minus plus excuse me, sine 2 pi k minus 1 times f naught divided by sine 2 pi f naught times 1 minus phi2. I'm going to write it this side on the other side so that we don't have any confusion. So where f naught is 1 over 2 pi cosine inverse of a over square root of a squared plus b squared, I believe. It's right here, and that is the system frequency. And that is the general expression for the ACF if we have complex roots in the characteristic polynomial. We call the characteristic polynomial because it explains the characteristics of the series. And keep in mind, if the roots are complex, there will be oscillations in the ACF. However, those oscillations are damped in the sense as h approaches infinity, the ACF would become zero, theoretically making the series causal and stationary in the weak sense.